Hello, everyone. My name is Simon Viel. I'm an assistant professor at Carleton University and the analysis coordinator for DEAP-3600 at SNOLAB. It's a pleasure for me to present our latest results. The DEAP collaboration has 95 researchers in 16 institutes in 9 countries. Our detector, DEAP-3600, is located in Cube Hall, more than 2 kilometers underground at SNOLAB. Here are a few pictures of the detector during construction. 255 light guides were bonded to the acrylic vessel, and at the end of each light guide is a photomultiplier tube, or PMT, looking inward towards the liquid argon volume. This detector is in a steel shell, and on top of the steel shell are 48 Vito PMTs looking into the water tank. This water tank serves as shielding as a muon Cherenkov Vito. DEAP stands for Dark Matter Experiment using Argon Pulse Shape Discrimination. The goal is to detect dark matter particles colliding with argon nuclei. So hypothetically, if a dark matter particle was to come in here and interact with an argon nucleus, it would induce a nuclear recoil. And along the track of the nuclear recoil, this would excite the argon into dimers. And when the dimer dissociates, it emits a scintillation light at the 128 nanometers. This UV light then travels to a wavelength shifting layer of the material TPB, which converts the light from UV to 420 nanometers. These visible photons then go in the light guides to be detected by the PMTs. DEAP has collected data in a stable way from November 1st, 2016 to March 28, 2020, when we emptied the detector of liquid argon because of the pandemic to get it into a safe state, but also to prepare for hardware upgrades. The lifetime fraction of the detector is shown here in blue for the dark matter search, and our overall downtime, shown here in white, is less than 3% over this whole period. When visible photons get to the PMT, they generate photoelectrons at the PMT cathode, which then generate a visible electric pulse. And so this is the average intensity in photoelectrons as seen as a function of time in the event. The de-excitation of the dimer generates scintillation light with a time constant depending on its quantum state. If the dimer is in the singlet state, this de-excitation time is 6 nanoseconds, leading to the very steep lifetime that you can see here. But if it's in the triplet state, time constant is much longer, 1.4 microseconds. Also visible in the pulse shape is after pulsing effects here in pink from the PMTs, and at later times, the longer time constant of TPB emission. The full pulse shape model of DEAP is documented in one of our publications here. This pulse shape, crucially, is different when we look at background-like electron recoil events compared to signal-like nuclear recoil events. In a nuclear recoil, there's more of a singlet state being excited, which means there's a higher fraction of prompt light in the event. Comparing that with the electron recoil type event, it generates more dimers in the triplet state, and so light is seen with longer time constant. We can define this variable f prompt as being the fraction of light in the prompt window, 60 nanoseconds, around T0, over the total amount of photoelectrons that are seen in the event. And so this is a 1D histogram of f prompt for neutron source calibration data. This is a log Y scale, so you can see we have a lot of background events from argon-39 beta decays with low f prompt. Whereas at high f prompt, we see the neutron scatters, which in this case are signal-like. When we look for dark matter, we take away this calibration source, and so we are sensitive to dark matter in that region in f prompt. DEAP, in fact, has world-leading PSD performance. This is documented in our latest paper here, where you can see the manuscript on the archive. In this paper, we considered 4 algorithms, and our best one is when PMT after pulsing is taken into account and removed to get a non-biased estimator of the number of photoelectrons. With this algorithm, for events at 110 PE, for example, this is the nuclear recoil acceptance as a function of F prompt, and the leakage probability for argon 39 as the function of F prompt. And we can see that at 50% nuclear recoil acceptance, the leakage probability is as low as 10 to the minus 10. This is what the data look like, and now taking F prompt as the y-axis, plotted as a function of number of photon electrons in the event. Dark matter region of interest is at high F prompt and very low PE, between 100 and 200 PE. A much higher PE, you can see full energy alpha decays, and one of the main backgrounds in the nuclear region band is from attenuated alphas and neutron scatters. This is the argon 39 peak here, or beta decay spectrum, and the gamma decay contributions are here. Focusing on the electromagnetic recoils here and taking a 1D histogram of the number of photon electrons here, you can see that our model for the argon 39 beta decay is very good. Data in gray agrees with the model in black. And likewise for the gamma spectrum, including this gamma line from potassium 40. In fact, higher up here, we can see the shape from argon 42, potassium 42, and allowing us to measure the specific activity of argon 42 in atmospheric argon with world-leading precision. Moving on to the backgrounds in the nuclear recoil band. Neutrons can create nuclear recoils, but sometimes they create multiple nuclear recoils in close successions, allowing us to veto the event. Likewise, if one of these neutrons, for example, for an alpha N process in the PMT class, creates a nuclear recoil, but then gets captured on hydrogen or gets captured on argon 40, which is the main isotope in the liquid argon target. And then afterwards, a capture gamma is seen in a close succession, allows us to veto the event. Otherwise, we have data control region, allows us to constrain this background, and the resulting background estimate agrees with simulation, taking material assays as input. Moving on to alphas, there are sometimes alphas in the liquid argon bulk. Those deposit their full energy into the liquid argon, and so they're not a background for the dark matter search because they have much higher energy. Here you can see that data in black agrees very well with our model, shown in orange. A little more worrisome are the alpha decays at the surface of the acrylic vessel, where some of the energy from the alpha gets deposited in the acrylic, and some of it gets deposited in TPB, and only some of it gets deposited in liquid argon. And this explains this tail here going towards lower photoelectrons detected. And so this would leak into the dark matter region of interest, except for position reconstruction, which allows us to reject the event. In fact, in DEAP, we have 2 main algorithms for position reconstruction. One is PE based. More PE are detected closer to the event. You can imagine a surface alpha where most of the light would go into one light guide, and so that PMT would see more light compared to an event happening in the center of the detector where the light would be more diffuse. And the second algorithm is time-based. The photons reach the PMT sooner when this PMT is closer to the event. Both algorithms agree very well between data and simulation, and also with an analytical model of the contained liquid argon mass as a function of the reconstructed radius. Overall, this allows us to select a volume in the center of the liquid argon target. That's inside what we call the fiducial radius. And this selected volume here has very low probability for surface alpha leakage, owing to our good position resolution. Those were the expected sources of backgrounds. Now moving to the unexpected source of backgrounds that we found during analysis. It turns out that there are trace amounts of dust particulates in the argon, and those can also create low PE events, but they originate in the center of the detector. Specifically when these alpha decays have a very short track length in the liquid argon, when most of their track is in the dust particulate, they can emit a low amount of light. And some of this light is also shadowed by the dust particle. This is now included in our background model. We have a pure control region for this background at intermediate PE. And you can see the overall rates here are very low. This is hertz per bin. Shown are the templates from the different particle size that are simulated, and the overall model agrees very well with the data. This hypothesis is further supported by XC2 measurement of metallic dust that we found in commercial grade liquid nitrogen that was used to flush the detector during construction. Another source of challenging background is from NEC alphas. These are polonium-210 decays in the flow guides. And under some conditions, a lot of the UV light is shadowed, resulting in a low PE event that reconstructs in the center of the detector. And so the three surfaces on which this can happen are the outer flow guide inner surface, the inner flow guide outer surface, and the inner flow guide inner surface shown here. And with the same color code, fortunately, there's a telltale sign for this kind of NEC events. Looking at reconstructed Z, so the vertical position in the detector from the PE-based algorithm, as a function of photoelectrons detected, you can see these arms features here in simulation that are seen also in the real data. So this allows us to define control regions and perform a template fit, the result of which you can see here. This is the new version of the template fit, where we also included a template for the dust alpha background, allowing us to constrain the rates of NEC alpha backgrounds very well and extrapolate to the dark matter region of interest. Fortunately, there are handles against these NEC alpha backgrounds. First is we have NEC veto fibers that are linked to PMTs in the NEC. And so when these PMTs see light from the fiber, we veto the event. Also, there can be internal reflection of the light, generating either excess lights in the top PMTs of the detector or early light, in which case we can reject the event. There's also the fact that the time-based versus PE-based reconstructed position disagrees between the two algorithms in the case of NEC alphas. So this is delta Z between the two algorithms, whereas the two algorithms agree well when in the case of argon-39 backgrounds or our simulation of dark matter events. And also, PSD is useful against these NEC alphas because these are full energy alphas. Still, it's just that the light is shadowed compared to a true low energy nuclear recoil that would be from a dark matter particle. And so in F-prompt versus photoelectrons detected, again, you can see this NEC alpha band and the dark matter band in green, and also the argon-39 band in blue here. This allows us to generate a region of interest for the dark matter search here. As you can see, there's a low number of photoelectrons detected, and the total number of background events expected in this region for 231 live days is less than one event. And so, did we see dark matter in the first year of DEAP data? No, we did not. This region of interest is empty of events for the November 2016 to October 2017 data set. This allows us to place limits on a spin-independent dark matter WIMP nucleon cross-section shown here on the y-axis compared to as a function of the WIMP mass. This result from DEAP-3600 is the red curve here with the excluded region at the top. So what we want to do in the future, analyzing more data, is pushing this down because dark matter could still be here at lower cross sections. We also reinterpreted these results. What's shown here is different dark matter halo hypotheses compared to the standard halo model. The standard halo model is shown as the black line in each of these. But if dark matter is predominantly in some of these different substructures of the Milky Way, the speed of dark matter particles can be different. And so for each of these different substructures here, you can see the speed distribution as a function of eta sub, which is the color scale. Here, it's the fraction of the dark matter that is potentially in this substructure. And so for each of these dark matter halo possibilities, we set the limit. Again, on the cross section of the function of mass, you can see the variation. Our standard result is shown here in black, and the variations are shown here in color. We also varied the dark matter coupling to protons versus to neutrons in isospin violating models. And actually, for some so-called xenon-phobic models, DEAP-3600 has world-leading sensitivity. We also looked at different operators in a non-relativistic effective field theory framework. Normally, we consider the O1 for the benchmark result, but the operator can be different. And so here shown are O11, O3, O8, O5, resulting in different limits on the cross-section limits as a function of mass. And we can see here examples for, let's say, a retrograde stellar stream. If this has most of the dark matter, the limits are shown here. Delta sigma over the standard halo model is shown here. Whereas for a prograde stellar stream, it goes in the opposite direction. So where to go from here? We have data collected all the way to March 28, 2020, 80% of which is blind since January 1st, 2018. To improve sensitivity, we trained multivariate analysis algorithms, random forest, Poisson decision trees, and a neural network, which is shown here. Those tend to have good performance against neg alphas. So these dark matter like events are shown in blue compared to neg alphas in orange. And when comparing the score here shown for the neural network between argon-39 data versus argon-39 simulation, there's good agreement between the two. So we're currently finalizing this analysis. Also, we're working on hardware upgrades. And so the main goals is to mitigate these limiting background sources in situ. We plan for a neck seal replacement, allowing a complete fill with liquid argon. New neck flow guides are being constructed with a pyrene coating, which is a slow wavelength shifter. This will allow us to remove the neck alpha background with PSD in analysis much more easily. We also install an alternate cooling system to filter out any dust particulates. And we also perform maintenance and cryogenic systems. And so this hardware upgrade has been delayed because of COVID, but we do plan to complete it in the next 6 months for first data with much improved sensitivity starting in January 2022. The longer term plan is to build larger detectors with the global argon dark matter collaboration. DarkSide 20K detector is shown here, which will have 20 tons in the fiducial volume, 50 tons of underground argon overall. And the collaboration is as partnered with DarkSide collaboration and other liquid argon dark matter collaborations towards reaching this goal. You can see here the sensitivity on the same axis is much better for DarkSide. And we're also planning the ultimate liquid argon dark matter experiment called Argo, which should go and have sensitivity all the way down to the neutrino floor. Argo is planned to be built and to see first data by the end of the decade. In conclusion, we are looking for dark matter with DEAP-3600. The detector performs very well and has sensitivity to new physics. The data analysis continues, and we have a multivariate analysis to improve signal acceptance. There are many new searches and measurements that I have not talked about here, so stay tuned. And also this hardware upgrade, which will vastly improve our sensitivity to dark matter starting in 2022. Thank you very much.